don't know why it wasn't working, but thank you very much for pointing that out in the chat, because then I figured it out. Woohoo! Okay. Awesome. Those intermolecular forces are looking good here. So a lot of you are identifying that right here we have a very polar molecule because it has a hydrogen bond, and I'm going to put it in quotes here because it's not actually bonding that we're talking about. We're talking about when I have a bunch of these OHs by one another and what that does for the molecule. It's those things in between that we were talking about again yesterday. So that one has hydrogen bonding. What type of intermolecular force would this one be?
Dipole, dipole, dipole.
Yeah, exactly. Thank you. Dipole, dipole. Beautiful. So we have to think about which of those holds the molecules closer together. So again, we don't want to talk about actual bonding, but we want to talk about the forces in between molecules. So the forces between these hydrogen bonded molecules versus a bunch of these molecules with just dipole-dipole would be held together more tightly with more force. Even though they're not like actually touching one another, they're not actually sharing or exchanging electrons, but they're being held in space closer together. Like if we had a container of water, okay, all of those different water molecules are individual molecules of water, H2O, but they're held together in our cup and not just going off into space as gases because of those hydrogen bonds. Okay, and again, bonds in quotes because it's not actually bonded. One molecule of oxygen and another molecule of oxygen are just near each other in the glass, not going off into space as far as they can. Okay, so they're being held with a force near one another. So we're not breaking bonds. Nowhere in your definition should anything include breaking because it's not actual bonds, okay? We're not taking a hydrogen off of the oxygen. We're just making them go further apart because when we boil, we're speeding up the particles so that they take up more space and they become gases. But it takes that force to do it. And it would take less of a force to overcome the interactions between the dipole-dipole than it would if it's got hydrogen bonding. So why don't you take a couple notes for yourself? We're going to get back to the notes that we were working on last week, so you can pull those out. That'd be a good place to write this stuff down. And one last time reminding you that your IA assignment part 1 should be due right now, actually a little bit ago. So make sure that that's in. The conference reflection I posted in one of the announcements, but I will repost it in the folder as well. And exit full screen. I'll look at adding it to the chat right now as well. Okay, I'm posting it in the chat as well, but it is on Schoology. Just by tomorrow, please. For those of you who haven't already done it. Okay, do we all have our notes? Good to go? Yeah, thank you for shaking your head. Excellent. So, Great question. Completely signed up for the IB exam registration. You should have gone through 2 separate sites to do it. And if you are concerned that it didn't work right, contact me. And it's different than the AP stuff. So if you're like, oh, I did the AP one, I'm good, you're not. You've got to go through the sites that are on Schoology. Good question. Okay, so let us exit and go back. Okay. So we're looking more at reactions today. And this is where we ended last Tuesday. Tuesday? Yeah, Tuesday, so long ago. So just as a little refresher for us, we know that alkanes are not very reactive, but we do know that it'll form a combustion reaction as long as it overcomes that big as long as it overcomes this big, ooh, well, that's exciting, activation energy. And we said that we needed to remember that a combustion reaction has something plus oxygen forming CO2 and H2O. So we said we don't want to forget that. And now we can move on to one other type of alkane reactions that we need to know about. So alkanes do undergo this thing called halogen substitution. Halogen substitution. Go ahead, type into the chat, what is a halogen? Ooh, we are digging deep into our brains from last year.
Okay, so I might be wrong, but isn't it like the fluorine, chlorine, like that, bromine, like that group?
Yeah, you got it. And one of the other answers was a group that's one away from the noble metal or that noble elements. That's perfect. Perfect. So those are the ones. Full screen snip. So just like you said, we've got fluorine, chlorine, bromine, iodine, technically astatine as well. So what do we know about those elements when they're on their own? Are they actually on their own? So if I have a fluorine,
doubles.
Yeah, there's going to be 2 of them. And I got another comment in here. They're super reactive. That's so true. They're so reactive. They don't want to be on their own. So most of the time, before they can find anything else, they find another one of themselves. And we call those the diatomic molecules. So all of these, when they're out in nature, unless they're bonded to a different molecule, they're going to be 2 of them, a diatomic molecule. Yes, they do desperately want 8 electrons in their outer shell, and they are so close. So true. So true. Let's see. Oh. Okay. Good. So what happens is that the diatomic molecule has UV light or really high temperature to break it apart. And once it's broken apart, it's what's called a radical. Because just like I read off of my chat here, they desperately want 8 electrons in their outer shell. So they're going to get really, really possessive. They're going to make a reaction occur because they're radicalized. Okay, and so the process is called a free radical reaction chain. And these halogens, depending on how many we have and how they're reacting, can replace more than one hydrogen on our alkane. Remember, we're talking about alkanes here. So we're talking specifically about what's happening on those alkanes. So we're going to replace hydrogens with halogens. I love the background, Zach. Just don't do that when you're actually in my lab, please. It looks like a few people are still writing this up, so I don't want to move anything yet. But it looks like we're getting close. And I know not everybody can have videos on, but it really helps me to be able to see how we're doing. So thank you if you're able to. Okay. It looks like most of the writing now. So we're going to go back here. And we'll talk about these different steps. So this free radical reaction chain has 3 steps, but those 3 steps can go on and on and on for a very long time. So the first step is called initiation. Initiation, so the initial step. Okay, the words actually kind of make sense for us. Initiation is that initial step. And that's where we produce, really, this should say halogen radicals. It doesn't have to be chlorine. The one that we're going to do a demo of is chlorine, or not a demo, but a writing it out of. So it produces a halogen radical, like chlorine. And then we propagate. We have the propagation step. And that's where we're producing further radicals, both organic radicals and more of the halogen radicals. And this can go on a whole bunch of times, forming a whole bunch of different types of molecules. But eventually we get to a point where all of the radicals have bonded with something else. And we get to the termination step, where the reaction itself is terminated. There's no further reactions going on. So hopefully those 3 steps, initiation, propagation, termination, hopefully you have something in your head that can relate to those different words. Like maybe you have initiation where you're starting with a new club and you have some sort of initiation into the club. Or we see that in movies with like fraternities. We're going through initiation right now, and then they do all sorts of stupid things because that's what they do during their initiation for some reason. Like that's what we can maybe think of with initiation. Propagation, you might know the word propagate. Okay, it keeps happening over and over and over and more and more and more. And then termination, you might think about getting terminated from a position. Okay, you're fired, you're ending your deal with it. Maybe you've watched The Walking Dead, and so you know that there's that part about the terminus where it's the end of the line of the railway. So hopefully you can think of some things that help you remember those 3 steps: initiate, propagate, terminate. because you'll need to know that order. But let's actually look at what it means. So over to the whiteboard here. So I need, again, something to overcome the attraction between my halogens first. I need something that's either going to be, or something that's going to be producing energy in some way to overcome the activation energy from that reaction. So I'm going to draw my little sunshine here, because most often this is happening in the atmosphere. And so the sun rays come down, give my chlorine diatomic molecule enough energy to break apart into two different radicals. And so the radicals we indicate with a dot, a big dot. It's not like the dots that we used in Lewis diagrams. It's a big dot that represents radicals. So they have been radicalized, and now they really want to bond with something. Okay, they need one more electron. They want to take something off. They are desperate, just like my chat comment was, okay? And what's easiest for them to do when they see this molecule here, and why don't we take a minute to review our naming? Type into the chat, please, what the name of that organic molecule would be. Awesome, you guys are speedy, nice. Yeah, there's 4 carbons and they're all singly bonded, so butane is perfect, well done. So what this radical does is it comes in and it says, you're mine now. And so it's gonna bond with the chlorine and the hydrogen. But that means that this butane is now a butane radical, really wanting to bond with something. So I'm going to redraw it. 3, 4, with a dot here, that now this is a radical. It's got an opening that really wants something to singly bond with it. Okay, so my initiation was up here. And now I have begun the propagation step. Maybe in space, the chlorine radical here ends up having enough energy that it's moving around, and it ends up hitting the butane radical with enough energy and in the correct orientation to form a bond. But what if it happens that it's coming over here and in 3D in space, they end up hitting over here? Would the reaction occur?
Would the chlorine take the hydrogen, so then you'd have the 2 of the HCl's, and then you'd have a double radical butane?
We could, absolutely. So yeah, it would just remove that one. So let's get rid of these. If that came in, it's not finishing or terminating the reaction, but you are absolutely right. It's going to come in and take that one off. So you're right, now we'd have another HCl, and now it'd have an even more radicalized butane. Radical.
Is that what you meant by like propagation, like could like go on for many molecules? Like, is that what you meant?
Yep, exactly. And we could be looking at many more organic molecules to start with too. Like there might have been another butane that now is going through the process as well. Right now we're just focusing on this one though. So let's say this time that my chlorine radical Well, both my chlorine radicals are gone, right? So something's got to happen. Maybe I had another chlorine that had that initiation phase with my UV light coming in and breaking them apart. Perhaps. So if that were the case, then I'd have another one of these radicals that could come along. And so what if I came in this way? Would it terminate? If I'm going through space this way. Not going to terminate yet. No, no, no. But it would keep the reaction going, so we'd keep propagating. So it's going to take that hydrogen there, chlorine, hydrogen, and now my molecule, my radicalized butane, has 3 different spots that it is very unhappy. Oops. Keep it consistent there. Okay, and I had another one here. Let's say I've got another one yet. More UV. So this one's going to split up as well. We are getting near where we could terminate. If all of these leftover chlorines, so we've got 2 that I made up here, 1 that I made there, if they all come in at the correct spots, then I can finally get to termination, but only if they do. So we're gonna say in 3D that we want it to, because this has gone on long enough. And we're gonna say that it's terminated with a Cl, C, H, H, C, H, H, C, H, Cl, C, Cl, H, and H. Now we need to name it. So go ahead in the chat, name this molecule. Oh, we haven't done halogens yet, have we? No, halogens are named pretty easily. So chlorine would turn into chloro. Fluorine would come into fluoro. Bromine would become bromo. Iodine would become iodo. And we're not going to do astatine because there's so little of it around. So we would start the name out with one of these. And we know that we're dealing with chlorines here. And we're dealing with 3 chlorines. So what prefix would I use for the chloro? Yeah, trichloro, very nice. Could I have the chlorines on different carbons? Yeah, so what do I need to include in this name? Yeah, some of you are already typing it in, the full name, that's beautiful. We need to include the numbers, yes. So we could either start counting from either way. So really we're gonna have 2 possible answers here. We could say that it's 1, 2, 4, or we could say that it's 1, 3, 4, and we'd have the right answer. Trichlorobutane. 1, 2, 4, trichlorobutane, and a whole bunch of hydrochloric acids, right? That's what our products would be. And there could be so many other things that are formed depending on how it propagates. I could have a radical of methane. Let's see. I was trying to decide between methane and methane. I could have a radical of methane that could actually bond with the radical of the butane. And then I'd end up with pentane. Still radicalized because it has these other two on it, but that's another thing. So we could get larger and larger molecules depending on how things hit. Okay, we know it has to have enough energy and it has to be in the correct orientation for the reaction to keep going. What questions do you have about the halogen reaction here? Guys, you just did a lot of good reviewing. Not only were we reviewing the organic naming, but also reviewing activation energy, halogens. Well done, folks. Let us now go back to the presentation. So we have two reactions that we need to know for alkanes: combustion and free radical reaction chain. And with the free radical reaction chain, we need to know that it's 3 steps. We initiate, then we propagate, and then we terminate. Alkenes are more reactive than alkanes. And that's because the activation energy on that energy level diagram. So we'll do screen. So back on this one, we're looking at that energy level diagram. And let's say combustion again, because we said that almost all organic molecules are going to be able to undergo combustion. So if we have a combustion reaction again with an alkene, so let's say we have C2H4, what would I need to react it with for it to be a combustion reaction?
H2O.
One of the products, yes.
Oh, shoot. Oxygen.
Yeah, O2, thank you. Perfect. So we need some O2 to react. And then here we have a much smaller bump than we did before. So my EA is lower. And you're right, H2O, and there's one other product. What's that other product?
Carbon dioxide.
Yeah, perfect. Thank you. Okay. And we could go through and we could balance that quite easily, but we won't right now. So we know that this would also undergo combustion, but because the activation energy is lower than it is for alkanes for any of the reactions, we have some other reactions that we need to know about. And the first one, besides combustion, is called an addition reaction. So we're adding things. Okay, the name helps us know what it is. So we are adding to the molecule. And the only way we can add to the molecule is to remove the double bond. So the double bond becomes a single bond. So now we have more places for something else to come in and take its place. So the general form, let's just pick our easiest alkene. So the one that I was writing up here is our easiest one, C2H4. So we'll say C, double bond C, and then we've got some hydrogens. So there's my first part. And then we're going to have some molecule that has two different parts to it. So we could have so many different ones. Let's just do, since we're doing general form, let's just do XY. Since it's general form, XY. So this double bond breaks. I now have C, C, H, 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 and H. And then this XY would break apart, and one of these carbons would have an X, and the other would have a Y. So that's my general form. Notice that there are no other products here. No other products because both reactants end up together. And just one product. Some of the common things that you would see for this XY could be something like a diatomic molecule that we were just talking about. So those halogens would be ones. So we've got Cl2, F2, Br2, I2. We could also have something like a non-halogen diatomic molecule, H2. We could also have, and often will, have HOH. Water. Water is going to be able to allow us to make an alkene into an alcohol. That's a really common reaction. So when we have water as this XY, that means we're going to have an alkene going to an alcohol. If we had this H2, we'd have an alkene going to what? What would it become?
Wouldn't that just become a regular alkane?
Yeah, exactly. Perfect. So that alkene would become an alkane, which if we have enough activation energy, we could go through that free radical process again with initiation, propagation, termination, and who knows what this alkene could end up becoming. It could become like hexafluoral ethane. Ooh, replace all those hydrogens with fluorines. Goodness gracious, so many things that it could become. Okay. So we are nearing the end here. Oops, that was the wrong one. I wanted this one. I'm going to go back here to remind us of these things down at the bottom. Your IA assignment part 1 was turned in before you came to class. Your conference reflection, which I put in the chat as a link, but it was also on Schoology as a link, that's due tomorrow by 9 a.m.